Given a partially filled 9 by 9 Sudoku board. Return true if the filled digits obey the Sudoku rules, no repeated digit in any row, any column, or any 3 by 3 box. First, a row check. The top row contains 5, 3, and 7, with no duplicate filled digit. Next, a column check. The first column also has no repeated filled digit. Finally, the top left 3 by 3 box has 5, 3, 6, 9, and 8, again with no duplicate. All visible checks obey the same rule across the board, so this example returns true. To validate a Sudoku board, we must ensure that the digits 1 through 9 never repeat in any row, any column, or any of the 9 3 by 3 subboxes. If you build this naively, you'll end up writing separate, bloated loops to scan the board over and over again for each individual rule. It's a messy, error-prone approach. We need a way to walk across the board exactly once, validating rows, columns, and boxes all at the exact same time. Our massive paradigm shift is to use a single hash set as a master security vault. As we look at any number on the board, we will dynamically generate unique string keys that describe its exact jurisdiction. For a number 4 sitting at row 2 and column 7, we manufacture the strings, for in row 2 and 4 in column 7. We toss these into our set. If we ever try to insert a key that already exists, our vault will sound the alarm. Validating rows and columns is easy, but how do we uniquely identify which of the 9 subboxes a cell belongs to without using complex conditions? We use integer division. By dividing our current row and column indices by 3, we compress the 9 by 9 board into a tiny 3 by 3 coordinate grid of blocks. Our row 2, column 7 cell automatically maps to block 02. This gives us our final, airtight security key, for in box 02. Now watch the trap snap shut. Later in our single scan, we encounter another number 4 on row 2. It tries to register the key 4 in row 2. But our hash set immediately objects, that exact key was already cached. Because a hash set can only hold completely unique values, its entry method instantly returns false. The security breach is caught, the loops halt, and we confidently declare the board invalid. By encoding our constraints into clear, descriptive strings, we reduce a terrifying mountain of conditional checks into a single, elegant pass. We scan the grid exactly once, filter out the blank cells, and let our hash set police the rest, delivering a perfect Sudoku validator with absolute maximum code readability. Let's jump into the code solution. We begin by spinning up a single hash set of strings called scene. This single container will act as our central ledger. Next, we write 2 standard nested loops to traverse our 9 by 9 grid, row by row, column by column. The moment our cursor encounters a blank space, denoted by a period, our code hits a quick conditional check and immediately skips past it. We only care about active digits. When we land on an actual digit, like this 7 at row 4, column 1, we instantly construct 3 unique security strings. We plug the character and indices straight into our code templates, generating 7 in row 4, 7 in column 1, and by running our fast divide by 3 bucketing math, 7 in box 10. These 3 strings perfectly describe the entire legal jurisdiction of this specific cell. Now we attempt to insert all 3 keys into our hash set. Instead of checking if the set contains the key before adding it, we use a beautiful shorthand efficiency trick. A set insertion can tell us whether the key was newly added, true means the key was accepted, and false means it was already in there. By placing an exclamation mark in front of our add calls inside an OR condition, we try to insert them all in a single line of code. As our cursor continues its march, it lands on another 7 further along on row 4. It constructs its keys and attempts to log the very first one, 7 in row 4. But our ledger immediately objects. Because that exact string was recorded earlier, the set rejects the duplicate insertion. This failure instantly trips our conditional trap. The board is compromised, our loops break immediately, and we exit the function returning false. If our cursor manages to weave completely across all 81 cells without ever tripping this conditional alarm, it means every single active digit on the board has verified its total uniqueness. The loops smoothly finish their execution, we drop down to our final line, and we return true. We verified a complete Sudoku matrix using a single structural sweep and zero redundant overhead. For the standard Sudoku board, the size is fixed at 9 by 9, so time is O of 1, we inspect at most 81 cells. Space is also O of 1 because the set can hold only a bounded number of row, column, and box keys. If generalized to an n by n board, this same structural scan would be O of n squared. The pseudocode is a single sweep. For every filled cell, manufacture its row key, column key, and box key. If any key is already present, return false immediately. Otherwise add all three keys and return true after the board is fully scanned.